Hello everyone, welcome back. Thanks for watching my video today. And in this video, we're going to talk about a couple more tests for convergence or divergence of infinite series. The first one we're looking at is called the integral test. Let's talk about what the integral test is. If f is a positive, continuous, and decreasing function for x greater than or equal to m, where m is a positive integer greater than or equal to 1, and a sub n equals f of x, then either both the infinite series and the infinite integral converge, or they both diverge. Okay? A couple notes on the side over there. One, you're going to always have to evaluate an improper integral, which we did back in chapter 6, topic 13. Also, on the exam, usually you have to state the conditions that the integral test can be applied, but not actually have to prove them, which is good news. So let's take a look at a couple of these. First one says, confirm whether the integral test can be applied to the series and use the integral test to determine the convergence or divergence of the series. Okay. So here's our first one here, n over n squared plus 1. And we need to make sure that it is positive always, continuous always, and decreasing always in order to apply this test. All right, so first off, let's make sure it's always positive. Well, we're going from 1 to infinity, so the numerator will always be positive. The denominator, you square anything that's positive, add 1, is still positive. So we can definitely say that f of n, if we say f of n equals n over n squared plus 1, we can definitely say f of n is always positive. Okay, that's 1. Secondly, we have to make sure it's continuous. Okay, the denominator will never equal 0 here. So there's not going to be any discontinuities. So therefore, it is always continuous. Third thing we got to show is that it's always decreasing. Okay, let's go back to chapter, I think 4 here, and increasing versus decreasing. What we had to do is we had to find the derivative. So let's do that. F prime of n equals our denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator, all over the denominator squared. Okay, so if we just do a little simplifying, it'd be n squared minus 2n squared, so 1 minus n squared over n squared plus 1 squared. All right, the denominator will always be positive no matter what. And considering n starts at 1, this will always be positive, and it'll always be bigger than 1, which means 1 minus that will always be negative. So we have a spot here where this is always negative over always positive, which means this is always going to be negative. Unless, of course, n is 1, then it would be equal to 0. But it's always going to be decreasing after when n is 1. So now we can say also decreasing for n is greater than or equal to 1. So our three stipulations are met here. Therefore, if we can show that the integral converges or diverges, then our answer will be the same. So let's set up our integral from 1 to infinity of n over n squared plus 1. All right, I'm going to need to probably do this using some substitution here. So u equals n squared plus 1. All right, so this would be 1/2 integral of 1 over u du, which is going to be 1/2 ln absolute value of u. But we're going to get it back into our n's here. So 1/2 ln absolute value. Actually, we could drop the absolute value because n squared plus 1 is always positive. So we can just make those parentheses from 1 to infinity. That's going to be 1/2 ln of infinity minus 1/2 ln of 2. So ln of infinity is going to just keep going to infinity much faster than ln of 2 does anything. So therefore, this one will diverge, which means this whole thing diverges. So we can say our summation of n equals 1 to infinity of n over n squared plus 1 diverges. All right, second one. Again, we got to kind of go through that same process here. Is it always positive? Well, we're starting at 3, remember. So this will always be positive. And this would be starting at 6 minus 1, which is 1, and going up. So this will always be positive. So this will always be positive, all right? By this, I mean f of n equals n over root 2n minus 5 will always be positive. Is it continuous? Well, the denominator would be 0 when 2n minus 5 equals 0, which is 5 halves. But we're starting above that. So yes, it will always be continuous as well. Lastly, our derivative. All right, so we have root 2n minus 5 times 1 minus n times 1/2 2n minus 5 to the negative 1/2 times 2 all over the denominator squared, which is just 2n minus 5. All right, do some simplifying here. We get root 2n minus 5 minus 1/2 and 2 cancel out. So it's just going to be n over root 2n minus 5 all over 2n minus 5. Getting a common denominator up top here, we're going to have 2n minus 5 minus n over root 2n minus 5 times 2n minus 5 which is simply n minus 5 over 2n minus 5 to the 3/2 power. Okay, so let's see here. If we start at 3, this would be negative, and then 6 minus 5 to the 3/2. So 6 minus 5 is 1. So the 3/2 is positive. So this is always going to be positive, no matter what. Okay? It's even if we got up to 9 or 10 or 11 or 12 or whatever, it's always positive. The numerator, if you put 3 in here, it'll be negative. That's good. That means decreasing. 4 would be decreasing. 5 would make it 0, which means not decreasing. Anything past 5, 6, 7, 8, 9, 10 will make the numerator positive, which means we'd have a positive numerator over a positive denominator, which means positive, which means our original function would be increasing. So therefore, we can say f of n is not decreasing for n greater than or equal to 5. So we say the integral test does not apply. We'll have to try to find a different way to see if that converges or diverges for this one. Maybe later on. All right, the last one, I have a little graph here of this, just so we can take a look at it. 1 over n squared plus 1. So again, we're going to say f of n equals 1 over n squared plus 1. Clearly, that's always positive, okay? The denominator will never equal 0 in the real system, so it's always continuous. I'm going to rewrite this as n squared plus 1 to the negative 1. So then our denominator, or our derivative here, would be negative n squared plus 1 to the negative 2 times 2n, or negative 2n over n squared plus 1 squared. Okay? The n starting at 1, so this will always be positive, which means negative 2 times n will always be negative. The denominator will always be positive, so this will always be less than or equal to 0. Actually, it'll always be less than 0 for all numbers. Okay? So therefore, we can say f of n is the three things that we want it to be. Positive, continuous, and decreasing for n is greater than or equal to 1. And we can now apply the integral test. Okay, so now let's apply the integral test here. So integral from 1 to infinity of 1 over n squared plus 1 dn. We hopefully recognize that as inverse tangent. All right, so this is going to be the limit as n goes to infinity of the antiderivative of 1 to b of 1 over n squared plus 1 dn. So it's going to be the limit as n goes to infinity, b goes to infinity, sorry. b goes to infinity of tangent inverse, or arctan, whatever you want to call it, of n from 1 to b. So it's going to be the limit as b approaches infinity of tangent inverse of b minus tangent inverse of 1. Okay, if we put infinity into that, we would get tangent inverse of infinity minus tangent inverse of 1. Okay, we've talked about this before. The tangent inverse graph is going to approach pi over 2 as it goes to infinity. And then from the unit circle, where is the tangent equal to 1? That's at pi over 4. So our answer is pi over 4, which means this sum converges as well. Because this converges, this has to converge. Okay. Just kind of remembered, we didn't really do this one the correct, it is right, but we didn't do it the correct way. We wanted to make sure that we do limit as b approaches infinity and 1 to b. So I really should have wrote this a little differently. It worked out the same way, and it's fine the way we did it, but if we want to be correct, we should have did it like that, the way we were taught back in chapter 6. All right, so that's it for topic 10.4. Now let's talk about a p-series. The next topic will introduce one of the most common series, the p-series. Fortunately, it's perhaps the simplest type of series to determine convergence or divergence as well. A p-series is an infinite series of the form 1 to infinity of 1 over n to the p. You can kind of see what it looks like there as we write it out, where p is some positive number. All right. First of all, let's just talk about recognizing a p-series. Which of the following are a p-series, yes or no? So we want it to look like 1 over n to the p. We can rewrite it as 1 over n to the p. It's a p-series, okay? So the first one, we can rewrite that as 1 over k to the 0.8. It doesn't have to be n, it could be k or any other letter. So yes, this one is a p-series. Second one, we can write that as 1 over 2 to the n. That is not what a p-series looks like. The n needs to be the base. The variable needs to be the base here. So this one is not a p-series. Third one, you can write that as 1 over k to the 4. So yes, that is a p-series. Fourth one, we don't have to rewrite it at all. It is what it is. And no, that is not a p-series. It has to be 1 over n squared would be a p-series. And the last one, remember, this is like 1 over k to the 1. So yes, this is a p-series. Okay, so how do we know if it converges or diverges? Simple. If it's a p-series and p is bigger than 1, it converges to some number. If it's not bigger than 1, it diverges. So let's take a look at A. We can rewrite this as sum from 1 to infinity of 1 over k to the 3/4. Clearly a p-series. 3/4 is less than 1. So what did we just learn? If it's less than 1, the series converges. Next one. 4 to infinity of 1 over n minus 1 squared. You might start thinking, well, this is not a p-series. Well, no, it actually is a p-series. Not that we'd want to do this. We'd want to just be able to recognize this. But if we did substitution here, which, again, we don't want to do this, but if we did, it'd be 1 over u squared. And then if we put 4 in here for n, we would just start this at 3. These two series are exactly the same thing. Okay, so I would never want you to really do this ever again. Just recognize that this is a p-series. Okay, and then p is 2, which is bigger than 1, so this converges. Last one. This is not a p-series, so we cannot use the p-series test here. P-series theorem to do this, but it is a series we might be able to do without that. We could think of it as 1 over e to the k, 1 times that, which means this is a geometric series. And geometric series, since 1 over e is less than 1, we can do this by doing 1 over, well, it's not 1 in this case, it'd be first term over, so it'd be 1 over e squared over 1 minus r. That actually would be the answer. Okay, so it does converge to some number here, whatever this would be, but it's not a p-series. Okay, number 4. Determine the convergence or divergence of the following p-series. You might be thinking, well, that's not a p-series. It doesn't look like a p-series to me. Let's rewrite it first. 1 plus, I can rewrite third root of 4 as 4 to the 1/3 power, right? Or 2 squared to the 1/3 power. I can rewrite this one as 3 squared to the 1/3 power, and then 4, oh, sorry, this is 1 over this. 1 over 4 squared to the 1/3 power, and 1 over 5 squared to the 1/3 power. So technically this is a p-series. It's 1 over k to the 2/3, or n, or q, or any letter you want to use. It doesn't matter. I realize I said k and wrote n, but it could be anything. So it's a p-series where p is 2/3, which is less than 1. And as we learned just last slide, if p is less than 1, the series diverges. Okay? And the last thing on the last slide here, no work to be done here, just one extra series called the harmonic series. This is a very special series. A harmonic series itself is actually just a very special p-series. It's a p-series where p is 1, right? And we talked about before, if p is equal to 1 or less than 1, the series diverges. So the green box there, that is your harmonic series. And the blue box there is just showing that it does diverge. Okay? So that is it for topics 10.4 and 10.5. Thanks as always for tuning in the video today, and we'll see you again next time.